Close your eyes for a moment. Imagine that the ground beneath your feet disappears. Not the floor of your room, but the ground of the entire world as you know it. Cities, fields, rivers with their names, forests you recognize, all of it erased. And in its place appears something so different, so vast and so strange, that the first reaction isn't fear but wonder. You're in the Jurassic. 150 million years ago. And the Earth you see from here looks almost nothing like anything you've ever seen before. Tonight we're going to travel to that world. To the world of dinosaurs in their moment of greatest splendor, when they dominated every corner of the planet with a diversity and an abundance that makes any modern ecosystem look pale in comparison. We're going to explore its landscapes, its seas, its skies. We're going to meet the animals that inhabited them, from the most imposing predators to the smallest and strangest creatures. And we're going to understand the geological and climatic forces that created that world and that eventually transformed it into something completely different. It's not a journey of data and dates. It's a journey of images and atmospheres, of smells that no one has smelled and sounds that no one has heard in 150 million years. It's the kind of journey best made slowly, in darkness, letting the mind construct the world that words describe while the body relaxes and sleep approaches from the edges of consciousness. The Jurassic wasn't a moment. It was a geological era that lasted approximately 56 million years, from 201 million years ago until 145 million years ago. To put that in perspective, all of human history, from the first hominids who carved stone in Africa until this moment when you're listening to these words, fits 200 times within the Jurassic. It's a time scale that the mind can't really comprehend, only represent symbolically and treat with the humility it deserves. The name comes from the Jura Mountains, on the border between France and Switzerland, where 19th century geologists first found rocks from that period in sufficient quantities to study them. But Jurassic rocks are found on every continent in the world, including Antarctica, and in them are written the stories of a planet so different from today's that recognizing it as the same requires a conscious effort of imagination and knowledge. Before entering the Jurassic proper, you have to understand where it came from. The period that preceded it, the Triassic, had ended with one of the 5 great mass extinctions in Earth's history. Approximately 201 million years ago, possibly a series of massive volcanic eruptions in what is now the Central Atlantic, altered the climate so dramatically that between 70 and 80% of all the species that existed at that time disappeared. The world that remained afterwards was a devastated world, with simplified ecosystems, with empty ecological niches waiting to be occupied. And the dinosaurs occupied them. Not suddenly, not all at once, but in a gradual process that lasted tens of millions of years, in which different lineages of dinosaurs expanded, diversified, specialized in exploiting specific resources that other groups couldn't take advantage of as efficiently. The Jurassic was the period when that expansion reached its maximum, when dinosaurs became the dominant terrestrial vertebrates in practically every ecosystem on the planet. But before the dinosaurs filled that empty world, you have to see what the world itself was like. And the world of the Jurassic was, in its geography, radically different from ours. To understand the Jurassic in all its extension, you have to go down to the soil. To the literal soil, the one the dinosaurs walked on, the one that held the plants that herbivores ate and that provided refuges where the small mammals of the era, which already existed although in a very secondary role, hid from the world around them. That soil was different from ours. Not in its basic chemical composition, which was essentially the same, but in what grew from it and what lived in it. The forests of the Jurassic were conifer forests in many regions, but conifers that don't look like the pines and firs we know today. There were araucarias, relatives of the current Chilean pines and the kauri of New Zealand, that reached heights of 30 or 40 meters and that formed dense canopies over the ground. There were ginkgos, trees whose closest living species, Ginkgo biloba, still exists today as a living fossil, an almost identical survivor of its Jurassic ancestors that modern humans plant in our cities without fully realizing that we're putting a tree from the time of dinosaurs on a 21st century sidewalk. The understory of the Jurassic was dominated by ferns. not the delicate ferns that grow today on the humid edges of European forests. Tree ferns several meters tall, with fronds that extended horizontally to capture the filtered light that reached them through the canopy of the araucarias. Ferns that covered the soil in dense carpets, that colonized the edges of rivers and the margins of lakes, that extended across floodplains and the slopes of mountains up to altitudes that today would be above the tree line. The conifers and ferns shared space with cycads, squat, tough plants with fronds that looked almost like pineapple plants, low plants that grew in the understory and on open ground where the canopy didn't block too much light. And there were benedictitals, a group of plants that are today completely extinct, plants that looked superficially like cycads or small palms but that weren't related to either of those groups. They were one of the dominant plant groups of the Jurassic, and their extinction at the end of the age, while some benedictitals survived into the early Cretaceous, remains one of the mysteries of paleobotany. The soil of the Jurassic forest was covered with decaying plant matter, thick beds of fern fronds and conifer needles that accumulated as the plants above them died and fell and were colonized by fungi and bacteria and the small arthropods that broke them down and returned the nutrients to the soil. Beneath that surface layer, the soil was probably rich in organic material, darker than modern soil, warmer because of the tropical climate and the high productivity of the vegetation. In the spaces between the roots of the giant conifers, in the hollow logs where fallen trees provided shelter, in the moist soil of the riverbanks, lived the creatures of the Jurassic forest, invertebrates of every size, small reptiles, and the tiny mammals that were keeping the nocturnal schedule that they would maintain for almost 200 million years until the Jurassic and Cretaceous ended with a meteor and they finally had their moment. The rivers of the Jurassic were different from modern rivers, deeper and wider because the climate was more humid and rainfall was heavier and more predictable. The river channels that cut through the Jurassic floodplains were sometimes several kilometers wide, with braided channels that split and rejoined as the water volume varied with the seasons. These rivers were highways for the large dinosaurs that followed them, that drank from them, that waded through them in their daily movements across the landscape. And the rivers were also where some of the most dangerous predators hunted. The great plesiosaurs and ichthyosaurs of the Jurassic seas were gone, replaced in the rivers by crocodilians that were sometimes even larger than Tyrannosaurus would be 100 million years later. The mers of the Jurassic world were warm, shallow, and extraordinarily rich in life. The Tethys Ocean, that warm inland sea that stretched between the continents as Pangaea broke apart, covered much of what would later be Europe and the Middle East. The waters of the Tethys were full of ammonites, spiral-shelled cephalopods that were related to the modern nautilus, belemnites, other cephalopods with straight shells like giant squid, and countless species of fish, sharks, and marine reptiles. The plesiosaurs were among the most spectacular of these marine animals. With bodies built like flippers and a neck that stretched in a way that defied physics but worked perfectly for hunting fish and other prey in the water, the plesiosaurs ranged from a few meters long to more than 12 meters. They were found in oceans worldwide and were among the most successful vertebrates of the Jurassic. The ichthyosaurs were another dominant group of marine reptiles, animals that looked superficially like dolphins, with a streamlined body and a tail that provided propulsion. But unlike dolphins, ichthyosaurs were reptiles, creatures that breathed air but had adapted to life in the water so completely that they rarely, if ever, left the water. They hunted fish and belemnites and other marine prey, and they gave birth to live young in the water, similar to dolphins. The early mosasaurs hadn't yet evolved. The sharks were still relatively small and not yet the dominant predators they would become. But there were plenty of other predators in the Jurassic seas. Large fish, ichthyosaurs, plesiosaurs, and on the coasts, crocodilians that hunted anything that came to the water to drink. The shallow seas left deposits of limestone and other sediments that today form some of the most important fossil-bearing rocks in the world. The Solnhofen limestone of Bavaria, which forms a continuous layer that was deposited in a shallow tropical sea of the Jurassic, has preserved fossils so detailed that you can sometimes see the outline of soft tissues, the details of feathers and skin impressions. When we know about the delicate details of Archaeopteryx, the earliest known bird, it's because a specimen was preserved in the Solnhofen limestone, its feathers and skeleton captured in the fine sediment that buried it after it died and fell to the sea floor. The islands that existed in these warm shallow seas supported their own ecosystems, different from the mainland, with species that evolved in isolation and developed unique characteristics. Some of these island ecosystems were dominated by marine reptiles. Others supported populations of dinosaurs that, isolated from the mainland populations, evolved different characteristics and different sizes. The sauropods were the largest land animals that have ever existed. The very largest, animals like Argentinosaurus, may have weighed up to 100 tons, as heavy as 20 adult elephants, with a length that stretched the length of a tall building. But even the more common sauropods were enormous. Brachiosaurus weighed 50 or 60 tons. Diplodocus was longer but lighter, a whip-like tail stretching behind a long but relatively slender body. These animals had evolved a body plan perfectly adapted to exploiting a food resource that other herbivores couldn't reach: the leaves at the very tops of the tallest trees. With their long necks and their high front legs, they could reach up to 40 meters into the canopy, stripping leaves from the upper branches of the tallest conifers. They swallowed the leaves without chewing them, and their massive gizzards, containing stones that they had swallowed to help break down the plant material, ground the leaves to a pulp inside their bodies. To support bodies of this size required an enormous amount of food. A Brachiosaurus would have needed to consume hundreds of kilograms of leaves every day just to maintain its body. But the Jurassic forests were so productive that this amount of food was available. The sauropods were so numerous that in some locations, their fossils are more common than those of any other large animal. The long neck of the sauropods was not, as was once thought, held upright like the neck of a giraffe. Modern analysis of the vertebrae suggests that most sauropods held their necks horizontally or only slightly elevated, reaching forward to strip leaves from the branches. This posture made more sense for their anatomy and required less muscular effort than holding the head up high. The plates and spikes of the stegosaurs are among the most remarkable structures in dinosaur anatomy. Running down the back of animals like Stegosaurus were 2 rows of large bony plates, probably covered with skin and richly supplied with blood vessels. These plates were probably used for thermoregulation, for absorbing heat from the sun or radiating it to cool the animal. They may have been used for display, for communicating with other stegosaurs. The function of the sharp spikes on the tail is clearer. They were probably used in defense against predators, a weapon that the animal could use by swinging its tail. The ankylosaurs, armored dinosaurs with bodies covered in bony plates and spikes, were another successful group of herbivores. With their low-slung bodies and powerful tails, some of which had a bony club at the end, they were probably well defended against predators. Their low height meant that they were feeding on vegetation lower to the ground, vegetation that the tall sauropods couldn't reach, allowing them to partition the food resources with the other herbivores. The predators of the Jurassic were diverse and terrifying. The largest, animals like Allosaurus, reached lengths of up to 12 meters and weights of 2 tons or more. With sharp teeth and powerful hind legs, they were built for hunting. But unlike Tyrannosaurus, which would evolve in the Cretaceous, Allosaurus was a relatively light, fast predator, probably capable of running at speeds that would exceed any modern land animal. Allosaurus hunted in packs, at least some of the time. Evidence from bone damage on dinosaur fossils suggests patterns of attack that would be consistent with multiple predators working together to bring down larger prey. A pack of Allosaurus attacking a young sauropod could potentially succeed, using their numbers and coordination to overwhelm their prey. But not all predators were large. The compsognathids were small theropods, some of them only a meter long, that hunted small prey, lizards, insects, small dinosaurs. They were the fastest dinosaurs, built for speed and agility. And the dromaeosaurs, animals like Deinonychus that would become more common in the Cretaceous, were already present in the Jurassic in some regions, small but fierce predators with a large sickle claw on each foot. The pterosaurs ruled the skies. These weren't dinosaurs, they were a separate group of flying reptiles that had evolved from the same ancestors as dinosaurs but that took a different evolutionary path. The earliest pterosaurs were relatively small, with wingspans of a meter or 2. But by the Jurassic, some pterosaurs had evolved enormous wingspans. Pterodactylus, one of the most well-known pterosaurs, had a wingspan of about a meter and hunted fish from the sea. But larger pterosaurs were already evolving, animals with wingspans that would eventually reach lengths that made them the largest flying animals that have ever existed. The advantage of flight for a Jurassic animal was enormous. From the air, a pterosaur could spot prey that ground-based predators couldn't see. It could travel long distances in search of food. It could nest in cliff faces or tall trees, places where ground-based predators couldn't reach. The evolution of flight in pterosaurs was one of the major innovations of the age, an innovation that would allow these animals to dominate the skies for the next 100 million years until they died out with the dinosaurs at the end of the Cretaceous. The small animals of the Jurassic, the mammals, the lizards, the insects, the amphibians, are often overlooked in accounts of the age because they were dwarfed by the dinosaurs. But they were present, they were diverse, and some of them would survive to inherit the world when the dinosaurs died. The mammals of the Jurassic were small, all of them smaller than a house cat, most of them smaller than a mouse. They were mostly nocturnal, living in the shadows and the darkness while the dinosaurs ruled the day. They probably ate insects, seeds, and possibly the eggs and young of dinosaurs. They survived by being small, by being fast, by hiding in burrows and tree hollows where the large predators couldn't reach them. The fossils of Jurassic mammals show the development of features that would become important later. The development of the jaw and the ear bones shows the transition from the synapsids of earlier periods toward the modern mammalian anatomy. Some of the Jurassic mammals show evidence of fur, preserved in the finest fossils, suggesting that they had evolved temperature regulation and the ability to survive in cooler climates. Some of these early mammals may have been warm-blooded, maintaining an internal body temperature like modern mammals. Others may have been somewhere between the cold-blooded reptiles and the warm-blooded mammals we know today. The fossil record doesn't give us enough information to know for sure. But the presence of these small mammals, surviving in the cracks and crevices of the Jurassic world, waiting for their moment, is one of the great stories of geology. The insects of the Jurassic were diverse and strange. The largest flying insects were smaller than in the Carboniferous period that preceded the Jurassic, but they were still abundant and diverse. There were beetles, flies, wasps, bees, mosquitoes. There were dragonflies, some with wingspans of 30 centimeters or more. There were termites, roaches, grasshoppers. These insects filled ecological niches at the base of the food chain, breaking down dead plant and animal material, pollinating the plants, feeding the larger animals. The evolution of the insects of the Jurassic was driving the evolution of the plants and the animals that depended on them. The development of specialized relationships between insects and plants, relationships of pollination and seed dispersal, were beginning to be established. These relationships would become more complex and more specialized in the Cretaceous and beyond, but their roots lay in the Jurassic, in the ancient interactions between insects and plants in the warm, wet world of that age. The climate of the Jurassic was not uniform. While it was generally warmer than today, there were variations. The polar regions were cooler than the equatorial regions, just as they are today. Seasonal variations meant that some parts of the world experienced wet seasons and dry seasons. The interior of large continents was probably drier than the coastal regions. The high altitudes of mountains would have been cooler than the lowlands. But even with these variations, the overall climate of the Jurassic was much more uniform than today. There was no permanent ice at the poles. The temperature difference between the equator and the poles was less than today because the pole was warmer. This more uniform climate drove a more uniform distribution of vegetation and life. Warm-adapted plants could grow at higher latitudes. Animals that were adapted to warm climates could live in regions that today are too cold for them. The atmosphere of the Jurassic contained higher concentrations of carbon dioxide than today's atmosphere. This would have contributed to the warmer climate through the greenhouse effect, but it would also have affected how plants grew and how they photosynthesized. Higher carbon dioxide levels meant that plants could grow faster and could survive in drier conditions. The forests of the Jurassic were more productive than similar forests would be today with lower carbon dioxide levels. The oceans of the Jurassic were also warmer than today's oceans. The bottom waters of the deep ocean, which today are filled with cold water that sinks from the polar regions, were warmer in the Jurassic because the poles themselves were warmer. This warmer ocean would have supported different patterns of ocean circulation, different currents, different upwelling patterns that brought nutrients from the deep water to the surface. The life in the Jurassic oceans would have been different because of these different physical conditions. The volcanoes of the Jurassic would have affected the climate. Large volcanic eruptions inject ash and sulfur dioxide into the atmosphere, which can temporarily cool the climate by blocking out sunlight. Some of the variations in climate during the Jurassic were probably caused by volcanic activity. But over the long term, the volcanic carbon dioxide that was released into the atmosphere would have contributed to the overall warmth of the Jurassic climate. The movement of the continents, driven by plate tectonics, was continuously changing the geography of the Jurassic world. As continents moved and oceans expanded, the distribution of climate zones changed. Regions that had been cold became warmer as they moved toward the equator. Regions that had been in the interior of Pangaea, cut off from the ocean, became coastal as the supercontinents broke apart. These changes would have driven the evolution of new species adapted to the new conditions. The day-to-day life of a Jurassic dinosaur was probably not so different from the day-to-day life of a modern large animal like an elephant or a hippopotamus. The dinosaur would wake in the morning, make its way to food and water, spend the day feeding and moving, and rest in the evening. It would interact with other members of its species, some cooperation, some competition. It would watch for predators and worry about protecting its young. A young Brachiosaurus, born weighing up to a ton, would have grown rapidly, adding body mass as it fed on the leaves of the high trees. As it grew, it would have integrated itself into the herd, learning the migration routes from older animals, learning where the water sources were, learning the safe places to rest at night where predators were less likely to hunt. An Allosaurus would start its day looking for prey. It would travel through the landscape, following trails that other Allosaurus had made, perhaps meeting up with family members or members of its pack. When it encountered herbivorous dinosaurs, it would evaluate whether an attack had a chance of success. Too large a herd, too vigilant, too many young with protective parents, these would be reasons to move on without attacking. A solitary young sauropod, or a weakened or injured animal, would be worth attacking. A tiny mammal, perhaps like Juramea, would hide in its burrow during the heat of the day, emerging at night to hunt insects and small invertebrates. It would be constantly alert for danger. Every shadow could be a predator, every sound could signal death. But it would also feel the joy of life, the satisfaction of a successful hunt, the comfort of its nest, the connection with its family. A female dinosaur of any large species faced the burden of reproduction. The energy cost of producing eggs, keeping them warm, protecting them from predators was enormous. Many eggs and young would not survive to adulthood. Some would be eaten by predators. Some would die of disease or starvation. But some would survive, and those survivors would carry their species forward. The social structures of different dinosaur species were probably different. Some, like the sauropods, probably lived in large herds, which provided protection through numbers. Others, like the large carnivores, were probably more solitary, coming together only to breed. The evidence of fossil trackways and bone beds suggests that at least some dinosaurs lived in family groups or herds, but the exact nature of these social groups remains speculative. The communication between dinosaurs was probably through visual and auditory signals. Some dinosaurs had crests or frills that could have been used for display. Some had tail structures that could have been used for signaling. Some probably made vocalizations. We don't know what they sounded like, but we can imagine that the world was not silent, that there were calls and roars and bellows that echoed through the Jurassic forests and plains. Reproduction in the dinosaurs was probably through eggs, like all modern reptiles and birds. The eggs were probably laid in nests, and there's some evidence that at least some dinosaurs may have cared for their young after they hatched. Fossilized nests with skeletons of young dinosaurs arranged around an adult suggest parental care. The bone structure of some young dinosaurs shows signs of healing, suggesting that injured young were kept in nests where they were protected and fed while they healed. The size of dinosaur eggs was probably proportional to the size of the adult animal, but much smaller. A brachiosaurus, weighing 50 or 60 tons, probably laid eggs that were a meter or two long. The incubation period, how long it took for an egg to hatch, is unknown, but it was probably weeks or months rather than the 3 weeks that bird eggs require. The growth rates of dinosaurs were probably rapid. Some evidence suggests that at least some dinosaurs, particularly the large sauropods, reached their adult size within 20 to 30 years. This rapid growth would have required enormous amounts of food, but the Jurassic forests were productive enough to support it. The lifespan of dinosaurs is difficult to estimate, but some paleontologists have suggested that the largest dinosaurs may have lived for 100 years or more. Long-lived animals have time to accumulate experience, to remember good feeding locations, to lead herds through migration routes that only the oldest animals remember. This might have made the oldest, largest sauropods important to the survival of their herds. The diseases of dinosaurs remain mysterious. Some fossils show evidence of infection or injury, but we can only guess at what diseases might have affected living dinosaurs. Some might have been similar to diseases that affect modern reptiles. Some might have been unique to the Jurassic world. The death of a dinosaur could come from many causes. Predation was one. Disease and injury were others. Starvation, if the animal couldn't find enough food. Thirst, if the water sources dried up. Drowning, if the animal was caught in a flood or in deep water. The fossils that survive are usually animals that died in favorable conditions for preservation. In river channels, in shallow seas, in tar pits where their bodies accumulated and were quickly buried. Most dinosaurs, when they died, were probably scavenged by predators and decomposed completely, leaving no trace in the fossil record. The end of the Jurassic came gradually, not suddenly. The climate began to cool as the Cretaceous period began. The seas retreated and advanced again in cycles driven by changes in sea level. The continents continued to drift, driven by plate tectonics. The vegetation changed as new plant families, particularly flowering plants, began to appear. The dinosaurs that thrived in the Jurassic didn't disappear when the Cretaceous began. They evolved. Some lineages died out, unable to adapt to the new climate and the new conditions. Other lineages evolved new forms, new specializations. The large sauropods became less common in many regions, replaced by other herbivores. New carnivores evolved, some of which would become even larger and more fearsome than Allosaurus. The mammals continued in their small, nocturnal existence, waiting. They had survived the Jurassic, had adapted to its conditions, and would continue to adapt to the conditions of the Cretaceous and beyond. They had no way of knowing that they would survive the next extinction event that the Cretaceous would bring, that they would inherit the world when the dinosaurs finally disappeared. The pterosaurs continued to dominate the skies, evolving into ever larger forms. Some of the Cretaceous pterosaurs, like Quetzalcoatlus, would reach wingspans that seem impossible for a flying animal, creatures that weighed as much as a small airplane and could soar on the wind currents above the Cretaceous landscape. The Jurassic ended not with a catastrophe but with a slow transformation. One by one, species changed, adapted, evolved. The landscape changed. The climate changed. By the time the Cretaceous was established, the world looked different, but the Jurassic had prepared it for what was to come. The fossils of the Jurassic tell us what we know. Without them, we would have no knowledge of the dinosaurs, of the pterosaurs, of the ancient plants and animals that lived in that distant age. The fossils are the only direct evidence we have of that world. A fossil begins when an animal dies in conditions that favor preservation. Usually, this means dying in water, in a river or a lake or a shallow sea. The body is quickly buried by sediment, sand, silt, mud, that protects it from scavengers and from decomposition. As more sediment accumulates, the pressure of the overlying sediment compacts the lower layers. Minerals from the groundwater seep through the sediment and replace the original minerals in the bone, tooth, and shell, transforming them into rock. The process is slow. It can take millions of years for a fossil to fully form. But once formed, the fossil preserves the structure of the original organism in minute detail. The intricate structure of a pterosaur's wing bone, the detailed anatomy of a small mammal's skull, the growth lines in a dinosaur's bone that tell us how fast it grew, all of these are preserved in the fossil. Different types of fossils preserve different information. A skeleton gives us information about the anatomy and the growth of an animal. Fossilized footprints tell us about the behavior and the movement of animals. Fossilized skin impressions tell us about the texture of the skin and sometimes about the coloration. Fossilized stomach contents tell us what an animal ate. Coprolites, fossilized feces, tell us about the diet and the digestive system. The Lagerstätten, the special fossil sites where conditions for preservation are particularly favorable, give us the most complete picture of ancient life. The Solnhofen limestone, the Como Bluff in Wyoming, the Liaoning fossil beds in China, the Morrison Formation, these and other sites have produced fossils so detailed that we can see feathers and skin impressions and even the color of dinosaurs in some cases. Paleontologists have spent centuries excavating and studying these fossils. With patience and careful technique, they extract the fossils from the rock, clean them, prepare them for study. They look for evidence of disease, of injury, of growth. They compare fossils from different locations and different ages to trace the evolution of species. They use radiometric dating to determine the age of the rocks that contain the fossils, establishing timelines for the evolution of life. The fossils are a window into the past. They don't show us everything. The soft tissues that would have covered the bones, the colors of living dinosaurs except in rare cases, the behavior and the sounds and the smells. But they show us enough to reconstruct a picture of that ancient world. And from that incomplete picture, we create stories, we build understanding, we satisfy our curiosity about the world that was. The history of dinosaur paleontology is the history of the growth of human knowledge. The first dinosaurs identified as such by humans were recognized in the 19th century. Richard Owen, a British anatomist, coined the term dinosaur in 1842, recognizing that these animals were a distinct group of fossil reptiles, not just oversized versions of modern animals. As the 19th century progressed, more fossils were discovered. In the American West, a fierce competition developed between paleontologists competing to find and name new dinosaur species. The Bone Wars, as this period is known, was characterized by dramatic discoveries, by dinosaur fossils being dynamited out of the rocks, sometimes by paleontologists stealing discoveries from each other. Out of this chaotic period came many important discoveries. Triceratops, Stegosaurus, Allosaurus, and many others were discovered and named during the Bone Wars. The 20th century brought more organized paleontological study. Museums funded expeditions to the fossil-bearing regions of the world. Paleontologists from different countries competed to find new species, but under more organized and less cutthroat conditions than the Bone Wars. The expeditions brought back dinosaur fossils that were studied carefully, that were used to develop theories about dinosaur behavior and evolution. The late 20th century brought technological advances that allowed paleontologists to study dinosaurs in new ways. Computed tomography scans allowed them to see inside fossilized bones without destroying them. DNA analysis, where it was possible, in rare cases of exceptional preservation, gave insights into the relationships between different dinosaur groups. Biomechanical analysis allowed them to estimate the strength of muscles and the speeds at which dinosaurs could run. The 21st century has brought even more advances. Scientists can now determine the color of some dinosaurs by analyzing the microscopic structures in fossilized feathers. They can estimate the growth rates of dinosaurs by studying the patterns in their bones. They can reconstruct the way that dinosaurs held their tails, their necks, their limbs based on the structure of the bones and the attachment points of muscles. With each new discovery and each new technological advance, the picture of the Jurassic becomes clearer and more detailed. We understand dinosaurs better now than paleontologists of the 19th century could have imagined. But there is still much that is unknown. Many species of dinosaurs surely existed without leaving any fossil record. The behavior of dinosaurs, their sounds, their colors except in rare cases, remain partly or wholly unknown. The fossil record is incomplete, and our understanding will always have gaps. The extinction of the dinosaurs at the end of the Cretaceous 66 million years ago was one of the great events in the history of life on Earth. An asteroid impact combined with volcanic activity fundamentally altered the climate and the environment, making it impossible for the large dinosaurs to survive. Only the dinosaurs that had evolved into the form of birds survived to inherit the world. But the Jurassic dinosaurs themselves didn't live to see that extinction. They had evolved and died, had been replaced by other dinosaurs over the course of the Cretaceous. The Jurassic dinosaurs were not the same as the Cretaceous dinosaurs. Allosaurus was replaced by Tyrannosaurus. The long-necked sauropods became less common. Stegosaurus disappeared and was replaced by ankylosaurs and other armored dinosaurs. The reasons for the changes in dinosaur faunas from period to period are probably related to climate change, to the evolution of new plants and new types of food, to the evolution of new predators. But also probably related to the simple random process of extinction. Species die out, whether or not their extinction is directly caused by changing environmental conditions. Other species evolve to fill the ecological roles left empty. The extinction of the dinosaurs at the end of the Cretaceous was not the end of dinosaur evolution. The birds that survived were dinosaurs, and they continue to evolve today. Every bird alive today is a dinosaur in the strict scientific sense. The evolution of birds from theropod dinosaurs is one of the best documented examples of evolution in the fossil record. The transitional fossils, Archaeopteryx, Microraptor, and dozens of others, show the gradual evolution of feathers, of wings, of the body shape of modern birds from the theropod dinosaurs of the Jurassic and Cretaceous. The extinction of non-avian dinosaurs at the end of the Cretaceous is generally attributed to an asteroid impact combined with volcanic activity. The asteroid impact created a crater 60 kilometers across in what is now Mexico's Yucatan Peninsula, and the dust and ash thrown into the atmosphere blocked out the sun, causing a nuclear winter that lasted for months or years. Plants died without sunlight. The herbivores that depended on plants died. The carnivores that depended on herbivores died. The climate was disrupted. The oceans were poisoned with acid rain. The magnetic field of the Earth was temporarily disrupted by the energy of the impact. But the mammals survived. The small, nocturnal animals that had been living in the shadows of the dinosaur world for 100 million years survived. Perhaps they could tolerate the darkness better than the large dinosaurs. Perhaps they could survive on seeds and insects and carrion while the plants died and the herbivores starved. Perhaps they were simply lucky. The discovery that dinosaurs had feathers was one of the most important paleontological advances of the late 20th and early 21st centuries. For most of human history, dinosaurs were imagined as naked, scaly reptiles. The discovery of fossilized feathers preserved in the Liaoning fossil beds in China showed that at least some dinosaurs, particularly the theropods, had feathers. Feathers served multiple purposes. They provided insulation, helping the animal to maintain a warm body temperature. They were used for display, for communication with other members of the species. On the forelimbs and tail, they provided the lift that made flight possible. The evolution of feathers was not a sudden change but a gradual process, with the earliest feathers being simple tubular structures, similar to the filiplumes of modern birds, that provided insulation. Over time, they became more complex, developing barbs and barbules, developing asymmetry in some cases to provide aerodynamic properties. The evidence for feathering in Jurassic dinosaurs is less complete than for Cretaceous dinosaurs. No Jurassic dinosaur fossils have been found with preserved feathers so far. But the presence of feathers in Cretaceous theropods and in the fossil record of bird evolution suggests that at least some Jurassic theropods probably had feathers as well. The small theropods almost certainly had feathers. Some of the large theropods, like Allosaurus, probably had feathers, at least on the arms or the back or the tail. The color of dinosaurs can be determined in some cases by analyzing the microscopic structures in fossilized feathers. These structures, called melanosomes, contain melanin, the same pigment that colors modern bird feathers. By determining the size and shape of the melanosomes in a fossil feather, paleontologists can infer the color of the original feather. Some Jurassic dinosaurs have been reconstructed with colors based on this analysis. A small theropod from the Cretaceous was determined to have been reddish-brown based on the analysis of melanosomes in its fossilized feathers. These color reconstructions give us a more complete picture of what dinosaurs looked like alive, even if the picture is based on analysis rather than direct observation. The evolution of feathers in dinosaurs solved an important mystery in paleontology. How did feathers evolve? What was the selective advantage of the earliest feathers, which would have been too short and too simple to enable flight? The evidence of feather evolution in dinosaurs shows that feathers evolved for thermoregulation, for insulation, before they evolved for flight. Once the structures were in place, once the advantage of insulation and display were established, the transition to use in flight was a natural extension of the existing structure. The relationships between different dinosaur groups are shown in a family tree, called a phylogenetic tree, that organizes dinosaurs by their evolutionary relationships. The dinosaurs of the Jurassic fit into this tree in ways that show how they were related to each other and to modern birds. The theropods, the bipedal carnivorous dinosaurs, are more closely related to birds than to any other dinosaurs. The most bird-like theropods were small, probably had feathers, and showed many features intermediate between modern birds and the larger carnivorous theropods. Some theropods were only a meter long. Others, like Allosaurus and later Tyrannosaurus, grew to enormous sizes. The sauropods form a group distinct from the theropods. They were all herbivorous, all quadrupedal, all shared certain anatomical features that grouped them together. The sauropods continued to evolve and diversify throughout the Jurassic and Cretaceous, with new forms appearing as others went extinct. The ornithischians, the group that includes Stegosaurus, Triceratops, and other herbivorous dinosaurs, were distinct from both the theropods and the sauropods. They shared certain features: a backward-pointing pubis bone, a different hip structure from the saurischians. The ornithischians were entirely herbivorous. The flying reptiles, the pterosaurs, are not dinosaurs but a separate group that evolved from the same ancestors as dinosaurs. The flying reptiles of the Jurassic ranged from small insectivores to large fish-eating animals. Some would grow to enormous sizes in the Cretaceous, but in the Jurassic the largest pterosaurs were still modest in size. The marine reptiles of the Jurassic, the plesiosaurs, the ichthyosaurs, the mosasaurs, are also not dinosaurs. They are a separate group of marine reptiles that evolved from terrestrial ancestors and adapted to life in the sea. They are often grouped with dinosaurs in popular imagination, but they are not dinosaurs in the strict scientific sense. The relationships shown in the phylogenetic tree are based on detailed comparison of the anatomy of different dinosaurs, on the analysis of shared features that suggest common ancestry. The closer two animals are on the tree, the more closely related they are and the more recently they shared a common ancestor. The phylogenetic tree is constantly being revised as new fossils are discovered and as new analyses of existing fossils provide new insights into the relationships between dinosaurs. Every new fossil potentially changes our understanding of how dinosaurs were related to each other and to modern birds. The development of dinosaurs over the course of the Jurassic shows a process of evolution in action. The early Jurassic was populated by relatively small dinosaurs, survivals from the Triassic with new species evolving as conditions changed. As the Jurassic progressed, dinosaurs evolved into larger forms, more specialized forms, more diverse forms. The early sauropods of the early Jurassic, animals like Volcanodon, were relatively small by later standards, only about 20 meters long. As the Jurassic progressed, sauropods evolved into larger forms. Brachiosaurus and Diplodocus, the iconic dinosaurs of the late Jurassic, were giants, but they were the products of millions of years of evolution from smaller ancestors. The evolution of the stegosaurs shows another pattern of gradual change. The early stegosaurs, like Huayangosaurus, were smaller and simpler, with smaller and simpler plates and spikes. As the Jurassic progressed, stegosaurs evolved into more specialized forms, with larger, more elaborate plates and spikes. The carnivorous theropods evolved into larger, more fearsome forms. Dilophosaurus, a Jurassic carnivore, was about 6 meters long. Allosaurus, which appeared later in the Jurassic, was larger and more powerful. But Allosaurus was still small compared to Tyrannosaurus, which would not appear until the Cretaceous. The pterosaurs evolved into larger forms as well. The early Jurassic pterosaurs were small, with wingspans of a meter or two. As the Jurassic progressed, pterosaurs evolved into larger forms, with some late Jurassic pterosaurs having wingspans of several meters. But even the largest Jurassic pterosaurs were small compared to the Cretaceous forms like Quetzalcoatlus. This pattern of evolution toward larger size, called Cope's rule, after the paleontologist who first noticed it, appears in many groups over long evolutionary periods. There is probably a selective advantage to being larger in many environments. Larger animals can eat larger food, can defend themselves better against predators, can migrate longer distances. But there are also disadvantages to being too large. The energy requirements go up, the population density must go down, the vulnerability to some types of events, like extinction, goes up. The evolution of dinosaurs shows that in some lineages there was an advantage to being large, so natural selection favored larger individuals, and over millions of years the species evolved into larger forms. But in other lineages, like the small theropods, smaller size remained advantageous, and these lineages remained small or even evolved to be smaller. The footprints and trackways left by dinosaurs provide information that bones and teeth cannot provide. They show us where dinosaurs walked, how fast they were moving, whether they were alone or in groups. A trackway of a large sauropod shows the path it followed, with prints deep in the ground showing the enormous weight it carried. Multiple trackways crossing each other show animals moving in different directions, perhaps at different times or perhaps at the same time, crossing paths. Some trackways show drag marks from the tail, while others don't. This might indicate that some dinosaurs held their tails up off the ground while others dragged them. Modern analysis of trackways, using computer modeling of the movement of animals, has provided estimates of the speeds at which different dinosaurs could move. Large sauropods probably walked at speeds of a few kilometers per hour, moving slowly through the landscape, feeding as they went. Smaller theropods were capable of running at speeds of 20 or 30 kilometers per hour. Nesting sites preserved in rocks show evidence of dinosaur reproduction. Some sites show fossilized nests arranged in colonies, suggesting that dinosaurs nested in groups, possibly with parental care. The arrangement of eggs in some nests suggests that eggs were covered and kept warm, possibly by the parents sitting on them as birds do today, or possibly by burying them in sand and relying on the heat of decay or of the sun to incubate them. Bone beds, sites where many skeletons are found together, suggest mass death events. Perhaps a flood drowned a group of animals as they tried to cross a river. Perhaps a drought forced many animals to gather at a shrinking water source and disease spread among them. Perhaps a volcanic eruption killed many animals at once. These bone beds tell us about the catastrophic events that can affect animal populations. Trace fossils, the fossilized evidence of activity, like burrows or feeding marks, tell us about the behavior of animals. Burrows of small dinosaurs or other animals show us where they hid. Feeding marks on bones show us which predators ate which prey. Tool marks made by scavengers show us that dinosaurs were eaten after they died. The complete picture of the Jurassic that emerges from all these types of evidence — bones, teeth, footprints, trackways, nests, bone beds, trace fossils — is more detailed and more nuanced than the picture we would get from bones alone. The dinosaurs were not static creatures in a static world. They moved, they ate, they reproduced, they died. They had lives and behaviors and interactions with each other and with their environment. The climate of the Jurassic changed over the course of the period. The early Jurassic was warmer and wetter than the late Jurassic. The late Jurassic saw periods of aridity, with some regions becoming drier and more seasonal. These climate changes drove changes in the vegetation and the animals that depended on the vegetation. The warm, wet climate of the early Jurassic favored the growth of large forests and the abundance of water. The rivers were full, the lakes and swamps were large, the ocean levels were high. In this environment, large aquatic animals thrived. The ichthyosaurs and plesiosaurs were numerous. The coastal regions were rich with life. As the late Jurassic progressed, the climate became more seasonal. Summer rains followed by dry seasons meant that some regions had abundant water only part of the year. Rivers dried up seasonally. The vegetation adapted to these seasonal droughts. The animals adapted as well. Some became migratory, moving to follow the water and the vegetation. Others developed physiological adaptations to conserve water. The aridity of some regions in the late Jurassic led to the development of deserts in some areas. The interior of continents, cut off from ocean moisture, became dry. The animals that lived in these regions had to adapt to the scarcity of water. Some, like the large sauropods, probably needed to migrate to find water. Others, like small nocturnal animals, were probably adapted to lives that required minimal water. The variations in climate within the Jurassic, from wet to dry, from warm to cool, drove variations in the evolution of dinosaurs and other animals. The animals that thrived in the warm, wet early Jurassic might not have been well adapted to the more seasonal climate of the late Jurassic. As conditions changed, new species evolved that were better adapted to the new conditions. The climate variations also drove the movement of the animals. Large animals like sauropods, requiring enormous amounts of food and water, probably had to migrate seasonally or even continuously to find enough food and water. The trackways and bone beds that we find preserved in the rocks might show the routes of these seasonal migrations, animals moving from one region to another following the water and the vegetation. The Jurassic world was not a chaotic, disorganized place. It had seasons, patterns, rhythms. The animals lived according to these patterns, adapting their lives to the cycles of the year. The vegetation grew and shed leaves, flowered and seeded, followed the cycles of the seasons. The animals moved through the landscape, hunted, ate, reproduced, died. The ecosystem of the Jurassic was complex, with many species playing different roles. The plants formed the base of the food chain, capturing the sun's energy through photosynthesis. The herbivores ate the plants, converting plant energy into animal biomass. The carnivores ate the herbivores, controlling their populations and ensuring that no single herbivore species came to dominate. The decomposers, bacteria, fungi, insects, broke down dead material and returned nutrients to the soil. Within this ecosystem, there were relationships of predation, of parasitism, of competition, of cooperation. A predator and its prey were locked in an evolutionary arms race, with the predator evolving better hunting strategies and the prey evolving better defenses. Parasites fed on their hosts without killing them, creating a balance between harm to the host and survival of the parasite. Different species competed for the same food or the same space. Some species cooperated, forming herds or packs. These relationships created a stable ecosystem, one that could persist for millions of years even as individual species came and went. But the ecosystem was not static. Evolution was always happening. Species were always changing. New species were always appearing while others went extinct. The ecosystem of the Middle Jurassic was different from the ecosystem of the early Jurassic, which was different from the ecosystem of the late Jurassic. But the basic structure remained the same. Plants, herbivores, carnivores, decomposers, all in relationship with each other and with their environment. The extinction of one species could affect the entire ecosystem. If a plant species went extinct, the herbivores that depended on it had to find other food or face starvation. If a herbivore went extinct, The carnivores that hunted it had to find other prey. If a predator went extinct, the herbivores that had been hunted by it could increase in numbers, potentially outcompeting other herbivores for food. The ecosystem was resilient, able to absorb changes without collapsing. But it was not infinitely resilient. Large, rapid changes could overwhelm the ecosystem's ability to adapt. A major climate shift, a period of intense volcanism, a meteor impact, these could change the ecosystem faster than species could evolve to adapt to it, leading to mass extinction. The legacy of the Jurassic is visible in the world today. The great mountain ranges that were building during the Jurassic, the Sierra Nevadas forming in the west, the Rockies uplifting in the interior, the Alps building in Europe, were inherited by later periods and still shape the landscape today. The basins that were forming, collecting sediments from rivers and lakes, became the oil and gas reservoirs that power modern civilization. The evolution of life in the Jurassic laid the groundwork for the evolution of life in the Cretaceous and beyond. The mammals that survived the Jurassic went on to dominate the world after the dinosaurs went extinct. The birds that evolved from theropod dinosaurs went on to become one of the most successful groups of animals alive today, with over 10,000 species. The plants that were evolving in the late Jurassic and early Cretaceous, the flowering plants, would transform terrestrial ecosystems. The insects that evolved to pollinate the flowering plants created relationships of dependence between plants and insects that continue today. The diversity of flowering plants and the insects that depend on them is one of the great wonders of the natural world, and it has its roots in the late Jurassic. The climate of the Jurassic, warm, with high carbon dioxide, with weak temperature gradients between the equator and the poles, left its imprint on how Earth's climate system works. The understanding of greenhouse climates, of how carbon dioxide affects climate, comes partly from studying how the Jurassic was so warm despite the sun being about 3 to 4% fainter than it is today. The fossils of the Jurassic are a record of evolution, a demonstration that life changes over time, that species adapt to their environment, that the world is older and more changeable than humans for most of history believed. The acceptance of the reality of evolution, of the age of the Earth, of the immensity of geological time, came partly from the study of Jurassic fossils. The Jurassic is part of the human story as well. It is part of our history as a species, of how we came to understand the world. The dinosaurs of the Jurassic that fascinated the paleontologists of the 19th century still fascinate us today. The wonder that we feel when we contemplate the size and the diversity and the strangeness of the Jurassic world is a wonder that connects us to the natural world, to the processes that created us, to the great age and complexity of life on Earth. The Jurassic period ended not with a catastrophe but with a slow transformation. The climate continued to change. The continents continued to drift. The seas rose and fell. The animals and plants that had dominated the Jurassic slowly gave way to new animals and plants adapted to the new conditions. The late Jurassic, the final period of the Jurassic Age, saw the appearance of new forms of life. The first flowering plants appeared, small and undistinguished, but the ancestors of all flowering plants that would come later. The first snakes appeared, small creatures that would evolve into the diversity of snakes we see today. The first birds were still around, evolving from their theropod dinosaur ancestors. The dinosaurs of the late Jurassic were different from those of the early Jurassic. New types of herbivores had appeared, new types of carnivores. The sauropods remained abundant, but they were being supplemented by other types of dinosaurs. The stegosaurs and ankylosaurs were common. The small theropods were numerous. The extinction of many species at the end of the Jurassic, an event sometimes called the Jurassic-Cretaceous extinction, was not as dramatic as some other extinction events. Not all species were affected equally. Some groups, like the dinosaurs, continued into the Cretaceous with relatively little disruption. Other groups suffered heavier losses. The causes of this extinction event are debated. Some paleontologists point to climate change, as the greenhouse effect of the Jurassic atmosphere began to weaken. Others point to the rearrangement of ocean currents as the continents drifted and the geography of the oceans changed. Some point to the effects of volcanism, which can change the climate by blocking out sunlight or by adding carbon dioxide to the atmosphere. Whatever the cause, the Jurassic ended and the Cretaceous began. The world changed, but it was a change that was gradual, that allowed life to adapt. The dinosaurs evolved into the forms that would dominate the Cretaceous. The mammals remained small, still waiting for their moment. The plants evolved into new forms, with the flowering plants slowly becoming more prominent. The transition from Jurassic to Cretaceous was not an abrupt line in time. It was a process, gradual and complex, of environmental change and evolutionary response. But for the purposes of geology, we mark a specific point, the boundary between the rocks of the Jurassic and the rocks of the Cretaceous, and call it the end of the Jurassic and the beginning of the Cretaceous. The study of the Jurassic teaches us about the nature of time and change. The Jurassic lasted 56 million years, a span of time that is almost incomprehensibly long from a human perspective. Our entire species has existed for only a tiny fraction of that time. Our civilization, with its cities and technologies and sciences, has existed for only a few thousand years, a moment compared to the Jurassic. Yet within those 56 million years, enormous changes occurred. Continents moved. Mountain ranges formed. The climate shifted. The life on Earth evolved into new forms. The dinosaurs dominated at the beginning of the Jurassic and dominated even more at the end, but they had evolved into different forms. The study of the Jurassic also teaches us about the interconnection of all things. The climate affected the vegetation, which affected the herbivores, which affected the carnivores. The movement of the continents affected the climate, which affected evolution. The volcanic activity affected the atmosphere, which affected the climate, which affected life. The study of the Jurassic teaches us humility. Our species is young. Our civilization is very young. Our understanding of the world is partial and incomplete. We know a great deal about the Jurassic, but there is much that we don't know. The fossil record is incomplete. We can't observe dinosaurs directly. We can only infer their behavior, their appearance, their ecology from the evidence we have. Yet within these limitations, we have reconstructed a picture of the Jurassic that is increasingly detailed and accurate. We know what kinds of plants grew in the Jurassic forests. We know what kinds of animals lived there. We know roughly how fast they moved, how they reproduced, what they ate. We have constraints on what they could have been and what they could not have been. This knowledge comes from the careful work of paleontologists, geologists, and other scientists who have dedicated their lives to understanding the past. It comes from the fossils that are preserved in rocks, fossils that were created by chance. A dinosaur had to die in the right conditions for fossilization to occur, and millions of years had to pass for the fossil to be exposed to modern humans to find. It comes from the willingness of humans to ask questions, to be curious, to imagine worlds that we have never seen and can never see, and to work patiently to understand them as completely as we can. The Jurassic world was not peaceful. It was a world of predators and prey, of life and death, of struggle and survival. But it was also a world of incredible beauty. The towering araucarias reaching toward the sky, the great dinosaurs moving through the landscape, the pterosaurs soaring on the wind currents above, the intricate details of the smallest creatures, all of it combined to create a world of overwhelming complexity and beauty. We can't experience that beauty directly. We can only imagine it, based on the evidence of fossils and the understanding of geology and paleontology. But the act of imagining it, of constructing the Jurassic world in our minds, is itself a profound human experience. The Jurassic is not just a time and a place in the distant past. It is also a way of seeing the world. It teaches us that the present is not permanent, that great changes are possible, that life is vastly more varied and more interesting than it often seems. It teaches us that vast spans of time existed before humans, and vast spans of time will exist after us. It reminds us that we are not the center of creation, that we are latecomer to a world that has existed for billions of years and will continue to exist for billions of years more. It reminds us that our species, for all its achievements and all its power, is a brief chapter in a much longer story. The Jurassic is within us. The iron in our blood comes from the iron that was in the Jurassic oceans. The oxygen we breathe comes from the oxygen produced by the plants of the Jurassic and all subsequent times. The calcium in our bones comes from the calcium that was in the rocks of the Jurassic world. We are made from the matter of the Jurassic, reconstituted, rearranged, incorporated into a new form of life. The Jurassic is in the birds that sing this morning. It is in the plants that shade our cities. It is in the rocks that we build our houses from. It is everywhere around us, waiting to be noticed, waiting to teach us about the deep history of the world we live in. The last days of the Jurassic would have been indistinguishable from the first days of the Cretaceous. There was no apocalypse, no great catastrophe to mark the transition. The sun rose and set. The animals woke and hunted and ate and slept. The plants grew and reproduced. The seasons turned. But imperceptibly, gradual changes were accumulating. The climate was shifting. The oceans were changing. The continents were moving. The evolution of life was producing new forms while old forms gradually faded away. An observer at the moment of the Jurassic-Cretaceous boundary, if such an observer could have existed, would not have noticed anything special about that moment. It was not a moment of crisis or of revolutionary change. It was simply a continuation of the gradual process of change that had been occurring throughout the Jurassic and would continue throughout the Cretaceous. But for us, standing at the boundary of the Jurassic period and looking back into it, the Jurassic is a distinct world, a world with its own character, its own special characteristics. The Jurassic is the world of the largest animals that have ever lived, of the sauropods that define the age. It is the world of the stegosaurs and their strange plates. It is the world of the pterosaurs beginning their evolution toward becoming the largest flying animals of all time. The Jurassic is the world in which the first birds evolved from theropod dinosaurs. It is the world in which the first flowering plants appeared, the ancestors of all the diversity of flowers and fruits and seeds that dominate terrestrial ecosystems today. It is the world in which the mammals, small and nocturnal, began their long wait for the extinction of the dinosaurs that would give them their moment. The Jurassic is a window into the past, a glimpse of a world that was radically different from ours, inhabited by creatures that were stranger and more wonderful than modern imagination easily conjures. It is a reminder that the present is temporary, that change is constant, that the earth and life upon it are far more ancient and far more extraordinary than our everyday experience suggests. The Jurassic ended 56 million years before the first human walked the earth. But in understanding the Jurassic, we understand ourselves. We understand where we came from, what processes created us, what forces shaped the world we live in. One final image before sleep takes over completely. It's dawn in the late Jurassic. The sky to the east tingles with pink and orange, the same colors that dawn produces today because they depend on the same physics of light scattering in the atmosphere. The araucarias are silhouetted against that sky like dark shapes that become defined as the light grows. The river that runs nearby sounds different at dawn than during the day, clearer, more present, because the other sounds of the world have not yet begun. A group of brachiosaurus is drinking at the bank. Their enormous bodies are reflected in the quiet water at the edge, where the river widens before a bend. They drink slowly, with deliberate movements, without hurry. The dawn illuminates them from behind and produces orange flashes on the hair that covers parts of their skin. They are the largest animals that have ever existed on the surface of the earth, and at this moment they are simply animals drinking water at dawn. A pterodactylus takes off from a nearby rock, beating its membranes with the soft sound of something opening to the air. It ascends in spirals, gaining height, until it finds the current of warm air that the rising sun is beginning to create over the plain and glides on it for a while without beating its wings, with its eyes fixed on the river that glimmers below. Somewhere in the forest, something moves among the roots of an araucaria. It is small, nocturnal, with eyes still large from the night that has just ended. It has survived another night in the world of giants. Tomorrow it will do the same. And the year after. And in 10 generations, and in 1,000,000 years, its descendants will still be small and nocturnal, waiting in the margins of the world of dinosaurs for a moment that none of them can imagine because mammals still don't imagine that way. They simply exist. They simply survive. They simply pass their genes to the next moment. The sun rises. The Brachiosaurus finish drinking and move toward the forest where the araucaria crowns are most accessible. The pterodactylus has disappeared downstream. The small mammal has retreated back into its burrow under the roots. The river continues to flow toward the sea, carrying sediments that one day will become rock, that one day will be exposed by erosion, that one day will be excavated by someone who doesn't yet exist and who will pull from it the bones of these same animals. The Jurassic continues. It will continue for another 50 million years from this imagined dawn. And then it will end, as all things that last long enough end. But this morning knows nothing of that. This morning is only this: growing light, flowing water, animals that drink and fly and hide, the world being completely what it is in the only moment it has. May that completeness accompany your sleep tonight.